Good morning, everyone. Welcome to this session. My name is Anita Hicks, and I'm Director of Marketing at Qualcomm. I am the MC for this session. A few housekeeping briefing items. Please silence your mobile phone. 10-minute breaks are scheduled at the end of each session, so we want to stay on schedule, so please try to be seated, which I think you all are. I think we're just going to do Q&A as you go along.
That's right.
Instead of a set time at the end. And then please fill out your session survey form. There'll be an opportunity for one of 14 winners of a 32-inch LG Smart TV. The drawing will be held in the Golden Gate foyer each day. Thursday, today it'll be at 5:30 p.m. and Friday it's going to be at 5:05 p.m. So that's all I have for the housekeeping items. So we can go ahead and get started.
Excellent.
And I want to introduce Kareem Yagmour, CEO of Operasys Incorporated.
All right. Thanks. Okay, good morning, folks. So in the coming hour, what I'm going to do here is walk you through how you can actually debug Android and check some of its performance at the platform level. So obviously there's only so much I can do in 15 minutes, but I'm hoping that this gives you a broad enough view of what is possible in order to enable you to kind of know where you need to search for more information. Before I get started, I would just like to have a show of hands here for the following questions to help me size up the group here. So who's got any sort of application development experience? All right. Platform development experience? All right, a good chunk. Excellent. Linux kernel development, the drivers / embedded Linux? Okay, good. Excellent. A pretty good chunk. All right. So just a little bit of background about myself before we get started. So I wrote the Embedded Linux book for O'Reilly about a decade ago. Last year, we published the Embedded Android title. I've been involved in open source for about almost 20 years now. Essentially, I'm most widely known in the open source community for having written the Linux Trace Toolkit, which was one of the first, if not the first, tracing tool for the Linux kernel. And if you look in the kernel sources for my name, you should find it relatively easily until somebody figures out that what I wrote was bit rotted and removes it away, which will eventually happen. And the most important thing I want to say here is that two things. First, I don't take myself very seriously, so if you have any questions while I'm going through this, please feel free to voice them. And the second thing I'm going to mention is this is a learning experience for me also. Android is a very complex system. I know a lot about it, but I don't know everything. So if you have anything that you want to add to what I'm saying, please feel free to share it. And I'm happy to have other people benefit from this. All right. So what am I going to talk about? The first thing I want to talk about is just an architectural recap here. I do want to spend as much time as possible on this, but I do want to make sure we're all talking about the same things. So I'm going to talk about some of the basics of the architecture, make sure we understand where everything fits, and then I'll move straight into, okay, how do I now, say, for example, get Eclipse to recognize my AOSP sources and go from there. Okay? Then we'll talk about, native stuff and kind of going higher up the stack as we move forward. And we do have, I think, just 50 minutes, so it's a tight squeeze, but we'll try to make everything fit in here. All right. And the other thing I'm going to do is I'm going to use the same board that was shown by Mr. Mollenkopf this morning, the IFC board, for some demos. It's a pretty good board and relatively affordable for anybody that wants to get their hands dirty with this kind of stuff. And I'm just going to ask the folks in the back if they could switch over to the table here to show the board to everybody. If 1, 2, yeah. No, guys, can you just switch to the board for a second? There we go. That's the board. Sorry, the mouse is not part of the board. It's just there to keep it from moving away because it doesn't actually hold in place. So you've got in there an 8060, so you can see it doesn't have an LCD panel. That doesn't stop us from doing any sort of the platform stuff that we need to do here with Android, because a lot of it actually doesn't revolve with visuals. But you can obviously, strap on visuals if you want to. And ultimately, you could use VNC if you really wanted to do, kind of not have an LCD there. All right. So let's switch back to the computer, and I'll continue from there. All right. So. Right, there's plenty of information about the board on the net, and again, I strongly encourage you to take a look at it. Very nice board for the price point, and especially the processor that it has on there. Okay, some architecture basics, just making sure everybody here is speaking the same language. So Android as an operating system was not created with a generic kind of device in mind. It was created with one very specific device in mind, and that is phones. And everything in the stack reflects this architecture from which we're starting from. Okay, so obviously imagine here that we've got a Qualcomm chip that has the baseband processor and the SoC. Obviously, the classic model is you've got two chips, one doing the baseband, the other one doing the actual application side on Qualcomm processors that happens to be on the same die, and obviously that's one of the biggest benefits that you've got. But essentially, Android here is running on the SoC, all right, on the application processor. The baseband processor is running some other operating system, which is then used to actually talk to the cell tower, okay? So that's on the hardware side. And by the way, there are other versions of the slide on the net if you want to grab them today. And these slides have been sent off to the conference folks, so they should be available. I'm not sure exactly the mechanism, but they should be available to you. Now, if you take a look inside the actual SoC, obviously there's a whole bunch of processors or components in there that are connected to some sort of networking in fabric, okay? And the advertised speeds are usually the speed of the CPU cores. The other elements are usually not running at that same speed, but you get the idea of where this is going. Now, the software that you've got on top of this, in the case of Android, is something like that. The gray stuff, or at least I'm trying to kind of use some color coding here to make it simpler. Gray stuff is in C, yellow stuff is Java, but has to do with the system. Orange stuff is regular applications, okay? So at the bottommost level here, you've got the Linux kernel. So this is the same Linux kernel that has existed since 1991. What they've done in the case of Android is they've enhanced it in a number of ways. They've added features to it that leverage what's already in there. So for example, with regards to power management, all right, this laptop here that runs Ubuntu, if I close the lid, it'll suspend. I need to manually do something to actually get the power management to kick in. On a regular phone, you don't want that, okay? When you don't want the user to just go ahead and flip a switch on and off. That makes no sense whatsoever. You want to aggressively put the device to sleep as often as possible and as early as possible, all right? So they added a mechanism called early suspend, and that mechanism's job is to do exactly that. Suspend the phone as often as possible and as quickly as possible. Obviously, sometimes the user is doing something on the phone, so you don't want the phone to suspend. So they invented a reverse mechanism, which is called the wake lock mechanism, and that, once it's grabbed, allows the device to stay awake until all wake locks are released. Okay? So that's one of the features they've added to the Linux kernel. It is by far the most contentious feature they've ever added. So I've been involved in my fair share of Linux kernel flame wars. They usually span 200-300 emails. And that one spanned 2,000 emails and was not resolved even at that point. Ultimately, that feature and a lot of the other features were somewhat massaged back into the Linux kernel because Linus at the 2011 kernel summit in Prague said, look guys, they're shipping this thing on 1 billion devices. We can't keep excluding this from the kernel. We got to find a way to bring it back in. So the wake lock mechanism got merged and the early suspend got merged under different names. And the running joke between kernel developers is if your patch gets refused, just resubmit it under a different name. So anyway, so it's not wake locks, it's wake sources, and it's not early suspend, it's auto sleep. So anyway, and then they've got a whole bunch of other things like low memory handler, which preempts the out-of-memory killer of the Linux kernel. The out-of-memory Linux kernel, by default, is something straight out of a Tarantino movie. It's really stupid, wakes up, finds the process using the most amount of memory, kills it, goes back to sleep. Not very intelligent. In the case of Android, we want to have a mode where the applications or the components that haven't been used in a very long time are the ones that get killed off. So this low mem thing that you see here is essentially preempting the default behavior of the Linux kernel to allow us to implement the behavior Android expects. We have the binder mechanism, which allows us to have what's called system services on the top here, and the system services are the core piece of Android. All right. If you want to think, in operating system architecture terms, Linux is a general purpose operating system. The Android operating system essentially has a general purpose, a object-oriented core, which is built on top of this general purpose operating system. And that object-oriented operating system is the set of system services that you see right there. Okay? That is the core of Android. If you read application developer documentation, it says the system does X or Android does X. It usually means something in those system services. So one of the core things, obviously, if you're doing platform development that you might want to be able to debug, or even as an application developer, something that you would like possibly to have some insight on is, okay, how do those things work? How do those algorithms in those system services operate? How do I control them? Or what's happening when I'm making a call from my app all the way down to the hardware layer? How does that kind of work? You go out of the Linux kernel. The first thing you meet on the left-hand side here is a set of libraries. A lot of those you probably already know about, WebKit and so on. The one that's unique to Android is Bionic, because in the standard Linux systems, the C library is usually glibc. In Android, it's Bionic. So Bionic has a lot of technical limitations, but its main feature is its licensing. It is BSD licensed, not LGPL licensed. And this is something that you'll see throughout the stack. They've made a voluntary effort to remove as much GPL and LGPL code as they could, transferred it into either BSD or Apache licensed software. Okay? We've got one of the most important departures from the classic Linux architecture is this hardware abstraction layer. This is how essentially Android understands hardware. Android does not know anything about drivers. It doesn't even tell you how to write your drivers. All it says is, here's a contract. If you give me a HAL module that obeys that contract, I can talk to your hardware. All right? And obviously, Qualcomm provides those HAL modules to their customers that they can then package into their handsets and boards and so on, so they can ship Android on those devices. Okay? But that's a major departure of the classic way business is done as usual in Linux. You've got a bunch of native daemons, same thing as regular Linux daemons, but they serve a different purpose. They have init and toolbox. And then above that, obviously, you've got Dalvik or Art, which is going to be the next thing. And on top of that, the most important thing running, as I said, is those system services. So there's about, say, upcoming Android L in the preview, they have about 80 or 85 system services running in that device. They keep adding 4 or 5 every other release, okay? And they really are the core of the system. Any important decision made by Android is made in those system services. They are interrelated, and they use the HAL layer to actually talk to the hardware underneath it, okay? So one of the things I'm going to try to show you here in a demo, if everything happens as it should be, then it's to show you how you can actually set a breakpoint in one of the system services, trigger the system service, and walk down from there in the Java side, okay? That's a very powerful thing to do if you can pull it off. Got the same Java API that we had before through the Apache Harmony project. And then you've got essentially the Android application developer layer, which is available to app developers that they can use to actually write their applications. Many of those APIs will turn around, use Binder, and talk to the system services. Okay? So you can directly talk to the system services sometimes, all right? But oftentimes the APIs will do that for you, and the actual API of the system service is hidden away and not exposed through the SDK. All right? So if you count the layers here, in between the call from an app to the actual access to the hardware, we've got about 7 or 8 layers of software. Okay? And that's pretty considerable. Especially, and as I'll show you later, that we're crossing Java to native C to then C in the kernel. That creates a lot of complexity there that you have to be able to deal with. Now, if you look at Binder a little bit closer, and I don't want to spend too much time on that because we've only got 50 minutes here, but the Binder driver at the bottom here starts off with the Linux kernel. It's not talking to any hardware. It's just an abstraction layer, so there's no hardware initialized. It's using RAM. And that thing is, you can think of it as a piping mechanism that uses IDs to link 2 endpoints, all right? Now, contrary to, say, in the IP world, like sockets, if you open a socket, you know that if you're talking to port 22, you've got a certain daemon listening on the other side, or, say, 443, you got a specific other daemon, or port 80, you got other daemons. There is no matching of those numbers. So the matching between a number and an actual service happens because of this process on the left-hand side, which is called the service manager. That's a daemon that starts in the beginning and allows the system services to register themselves and broadcast essentially the ID they have for specific string names. So you can say, okay, status bar manager is ID foo, right? And if an application, say the orange box there, wants to talk to a system service, it talks to the service manager, says, I want to talk to this guy here. Here's the string. Service manager to returns, gives it a binder ID, and then the binder ID is used to actually talk to that system service. Binder is the core of Android, as far as I'm concerned. It is a mechanism that dates back to BOS. So it went from BOS to Palm, and then from Palm to Android. And if you actually Google for Open Binder, you will find the documentation about the binder mechanism as it was open sourced by Palm before they killed off the project. And I was giving a talk 2 years ago at a conference, actually here in San Francisco, and I was kind of giving this explanation, and this guy raises his hand and says, "I'm the manager of Palm that killed it." So I said, okay, speak on, explain this to me. So apparently it was a mechanism that very few people at Palm actually liked. And he said the guys that, kind of open sourced it, then once they open sourced it, they left and all went to work for Google. So anyway, we've got Binder in Android, and it's an intrinsic part of the system. Now, the system services, as I showed you previously, they all look nice in a single box. However, they are actually housed in separate processes. And the process that's housing a system service doesn't really matter. It's more the fact that it is discoverable through the service manager that I was mentioning earlier. They do have separate processes, it seems, for isolating privileges and also for performance reasons. The gray boxes there are C system services. And if you kind of try to look for a pattern, it seems that anything that revolves around user interaction is written in C. So sensor service is in C. Surface Flinger, which has to do with rendering the graphics, is in C. Media playback is also in C. So it seems that they deliberately chose to write in C things that are not, that are time sensitive, all right, that the user can perceive as lagging if they were not responding fast enough. And those system services, again, if they want to talk to hardware, they'll go through hardware abstraction layer to actually do that. And again, one of the complexities of debugging things in Android at the platform level is being able to switch between all of those things, going from Java to C, from HAL to system service, and so on and so forth. If you want to take a look closer at the HAL, so the HAL layer essentially allows the Android stack to isolate the IP of the vendors in the HAL layers and allow them to essentially license it on whatever terms they deem is appropriate. Insofar as those modules exist and correspond to the proper API, they can actually talk to the hardware. Now, the complexity from all this stack comes from the fact that we're using different debuggers and different debugging environments for each of these layers. Okay? That's the hard part about Android. If you look at the kernel level, if you're doing any sort of kernel development, then what you're going to need is some form of Jtag Debugger. Okay, so that is a hardware piece, okay, that connects to the CPU core and allows you to essentially stop the core and set breakpoints and inspect stuff, okay. The kernel itself has some kernel debugging capabilities, but there are a lot of situations where the hardware is in a weird state and the kernel can't really comprehend it. But if you ask the hardware, it can give you a pretty good picture. So in the case of the Qualcomm devices, a lot of the times the Jtag Debugger is going to be the Lauterbach Trace32, whatever other device they have. You connect that to your board and you're able to step through your kernel code. Once you leave the kernel space, you can then use something like GDB Server, right? GDB Server is not something that's unique to Android. In fact, neither is Jtag. GDB Server is something that has existed and has been used in embedded Linux systems for 20 plus years. So this is just something that Android uses to allow you to debug the native side of things. However, when you move into the Java world, what you've got is Dalvik, and Dalvik has its own debugging capabilities, okay? And in those cases, you have to use Ddms, all right? So the trouble here is when I'm going from my app, trying to go all the way down to the kernel layer, okay, you have to cross 3 different debuggers. So I can have a situation where I have one breakpoint set in each of those debuggers, and yet it's the same code path, right? So I said step through the Java side, and then, run, and then it runs and hits my C breakpoint, and then from there onwards down the stack. Okay? So far so good? Alrighty. Now, in terms of development environment, ideally you would have something like this, all right, where essentially you're connected to your host, not just over USB, but also with some kind of Ethernet, all right, and serial. So serial will allow you to get the early kernel startup. Ethernet will allow you to boot from remote if the bootloader on the board is network capable. And as far as I understand, the bootloader on this specific board is not network capable. If it were, it'd be great. But if you got something like U-boot, it actually does this, okay? So, if you were able to network boot, you could essentially not flash anything on the board, just have the bootloader fetch an IP address using DHCP, use that IP address to get a kernel image, and then mount its file system over NFS. So when you build, you just press reset, and it gets everything off the host instead of us having to reflash every time, as we have to do, say, with fastboot, where we do fastboot flash all, and then you flash whatever it is that you've got to flash on the other side. So in terms of IDEs, you can use pretty much what you want. And the one missing here, and I kind of forgot to add it before getting this reviewed, is Intellij. So Android Studio can also be used to do a platform development. I've been holding off on it until they've made it as the officially released thing, as everybody can use it. And up until that time, I've kind of avoided it from my explanations. But most of the editors out there can be used. That's really up to you. So what I want to show you here as a first demo is how I can set up Eclipse to actually recognize my AOSP sources, all right, and be able to set breakpoints in there and go from there. Okay? So let me kind of go to my Eclipse here, which I've already set up. So I'm just going to walk you through some of the things that I've done, and hopefully we can then show you a debugging session. And then I've got corresponding slides there. But the most important thing is to actually see it in real life. So, okay, first things first. What I needed to do, sorry, let me just do this, switch this over to a color that you're going to be able to see. There we go. So let me do that, Eclipse. All right, so here we are in the Eclipse directory from the ADT bundle that I got from Google. So this is the same Eclipse that an application developer would use. All right. Inside this directory, there's an ini file, as you can see here. Okay. Now this ini file, let me open the one that comes from factory, so to speak. Okay. It's got a specific amount of heap size that it will tolerate. So this XMX variable there is the largest size of heap size it can deal with. That is not enough, or is not sufficient to be able to deal with the AOSP sources. Okay. We have to increase that. So what I did is I changed mine, and I'll show you what I've got on my side. So I set it at 1500 instead of 1024. Right? Otherwise, what will happen is if you try to actually tell Eclipse to go and munch on the AOSP sources, it'll crash at some point and report some unrelated Java error, but the problem really is the heap size. So once I've done that, I can then go ahead and essentially include my AOSP sources here in the Eclipse environment. How would I go about doing that? I could do something like this: new Java project. Okay. So then you follow with the wizard, except you tell it not to use the default location, but instead browse around until you get to the AOSP tree that you're interested in. So for example, in this case, this is the pristine sources of 4.4. So this is not the sources for this thing here. And then I would say essentially, so I've already got this imported, so this is why it's complaining, but I would say, finish, and then it would show up on the left-hand side. Okay? To make this work, you have to have what's called a class path file at the top level of the AOSP. Let me go show you what that is and explain to you how you need to tweak that. So if I go here in my, say, so here's my Inforce board. All right, I've got a .classpath file here at the top level. Now, whenever you get an AOSP tree from whoever, Qualcomm, Google, or anybody else, there is no classpath file at the top level. There is a sample one in one of the directories, and my slide has the path for that. So if you go to, if you look in Development IDE Eclipse, for example, there's a, actually, let me do this. There we go. There is a class path file in here that is given to you as an example. In my experience, and obviously this is not something that's a minus for any of the boards, but in my experience, none of those default class path files work as is. You have to go in and edit them, okay? Because the Eclipse, rules will not be able to comprehend your project just based on the default class path file. In fact, it'll just report errors. So you can see here, mine actually builds okay. So in other words, I got this triangle with the exclamation mark. If it did not build okay, I would have a red X saying, okay, this project has issues. All right. Once I've got the project on the left-hand side, there's cool things that I can do. So let me show you this. I can go, for example, into, for those of you who are maybe familiar with the development API, so if I go to Framework Core Java, say Android app, and I go for context impl here, I can look for get system service, all right? And for those of you who are familiar with the API, this is the call that you would make from the app developer API to get a handle on a system service and then start talking to it. Okay? So in Eclipse, once I've got this, I can do right-click and say, okay, open call hierarchy. And it's going to go around and look for everybody that calls this function, this method. Actually, it's a method, not a function. And I can do the reverse. I can also, so it's taking a little bit of time here, but it'll eventually show me a list. There's, as you'll see, there's actually a lot of calls to get system service. And right now it's selected for who is calling get system service, but the button right beside it is show me who get system service is actually calling. There you go. And then you can walk through that list. Okay. So this is relatively, this can be very, very powerful when you're actually traversing the AOSP sources. Okay, so this is how I can get Eclipse to recognize my sources, understand the classes, and so on. So far, so good? Yeah? All right. So in the spirit of staying, in the same context, even though in my slides I kind of cover it later, let me show you how I can actually now debug things, all right, in this environment, all right? And I'm going to use my board there to actually do that. So let me go here to Ddms. Okay, so Ddms is the Dalvik debugger. So I should actually have two things here. So I got the emulator started, and I also have the board. And what you see here when you select Ddms is all the Java processes which are on. You don't see the native ones. All right. If I were to shell into this thing and type PS, I would see processes which don't show up here because they're native. All right, or not. They're not running Dalvik. So in this case, if I want to latch on to, say, for example, a given system service, let me kind of select the system process here, which has the system services. And you'll see there's a column right beside it with numbers. That's the process number. And the column at the end is actually the port number on the host that you can connect to actually start debugging that remote process. And notice that when I actually move my mouse and I select one of them, it always has port number /8700. Okay, so 8700 is essentially the one that gets attributed to the one being selected. Once I've done this thing, I can actually start a debug configuration. So I can do, say, AOSP, IFC 6410 here. And what you should see is I should have a green bug that appears on beside my system process here. Give it a second. In fact, if I go to my debug view, he should have started trying to talk to the thing. So this is obviously a finicky process, so hopefully this actually does work. Otherwise, I might have to restart Eclipse, and I would do that and go back to the slides and come back to it. But usually this would, let me just double check that we've got the proper configuration here. So IFC 6410 says port 8700, that's the proper sources. Actually, just give it another try here. Maybe I actually didn't do it right. So selected this guy, debug. 1, 2. Houston. Oh, there we go. Oh, okay. So he has a problem, but he attached to it still. So you see that green bug on the left-hand side? That means the debugger attached. Let's see if he actually did the right job. He did. Actually, he is attached. He's got the whole list of threads. Okay, just took him a little bit of time. All right. So I'm attached to my system server process, which houses, as I said, the bulk of the system services. So what I'm going to do now is I'm actually going to go in the sources, and I'm going to set a breakpoint in, say, my status bar system service. So let me go ahead and just go to get the sources of that. So that is going to be inside, so framework-based services, so a little bit further down. Framework-based services, where's that? I went too far down. There we go, okay. Services Java, command root server, and let me go fetch status bar manager. There we go. So this guy here has a expand notification panel, and expand and collapse. And what I'm going to do now is I'm going to essentially go in my shell and actually trigger the system service. And you can do that for those who might be familiar with this, with the command line command which is called service. So I can do service here. And so, for example, if I do service list, it lists all the system services. And I can call upon some of those system services. I can do something like service call status bar 1, and that's going to invoke actually my status bar system service. Yes, I want to go into the debug perspective, and here we are. I'm essentially breakpointed in my status bar system service. All right, I can step from here. All right, so F6, 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 and so on. The board doesn't have a display, so you can't see what's happening, but essentially what's happened now is the status bar has expanded, right? And I've got a similar callback or similar breakpoint on the collapse. So if I do service call status bar 2, it'll collapse and it will trigger my breakpoint right there. Does that make sense? Right? So this allows me to plug into any piece of Java code that is packaged in my board. All right? So, and I can do this actually on both sides. I've done it here on the system service side, but I can do it on the actual, in the apps also. So for example, here if I select, say, my launcher, okay, COM Android launcher, I can also again do, start the debug configuration, all right? Yeah, okay, no, don't save those sources. Don't. Okay. And you can see the green bug has appeared, all right? And he is, sorry, in the debug side of things, he should have another virtual machine. So I have this one, I've got this other one now. And what I can do is I can go into Java sources, and then I can say, for example, okay, so in this case it's packages apps. So if I go into packages apps launcher, and then I go inside here, there's a launcher.java. Okay, and if I look for show all right, so show all apps is the call that gets called whenever you press the central button in Android to show all the applications, right? And at this point, if I had a UI and I clicked on that, I'd breakpoint before we actually get to see all the applications. The button would highlight itself, and I would break right there and be able to step from there, all right? And if that app calls the system service, I can have the corresponding system breakpoint the other system service, and then, you know, go back and forth between those two things. Okay, so that allows me to take control of all the Java side in the platform. Now, if I go back to my slides, I essentially have what you see here spelled out. So how to prepare Eclipse, by setting the class path, how to import it, and sometimes you have to fix things up. What you need to, in this case, I'm showing it with 4.3 how to do that, and then how you can browse the sources. And later on, I have essentially a set of slides that show you how to actually set breakpoints and go from there. Okay, so that's for the Java side. Now, in terms of the native side, okay, let's say I want to monitor things on the native side. What's available to me? So let me just quickly walk you through some of the tools that are available to us. So I can do something like here, like SCED top. This doesn't always work. We'll see if it actually works on this board or not. And I do have the older version of the BSP here, 4.1, not 4.4, which is the current BSP version. So yeah, it is not working here, but it might actually be working in my emulator. So let me try to show it to you there. So if I go back to this guy here, ADB E shell, actually not here, but the other one. So if I go to this guy, all right, SCED top, maybe it works here. I think it does actually. So what this does is, contrary to the regular top, it doesn't show you the current percentage of use of the CPU time, but more the cumulative use. So which process, since I started SCED top, has currently used the most amount of CPU. So that's one of them. Sorry about that. librank. So librank here allows me to see, actually be better in a shell. So librank here allows me to see the libraries in the system and how much memory is used by them and the processes that have those libraries mapped in their address space in any way, shape, or form. And let me kind of just do this. So that librank less. So, and you will see those VSS, RSS, PSS, USS acronyms when you use those tools. For those of you not familiar with those things, so VSS is the virtual set size, so how much virtual memory is being used. RSS is resident set size, so essentially how much RAM. PSS is the proportionate set size, and that one's a little bit hard to understand, but let's put it this way. If I have a library that is mapped by 10 processes, and that library measures 1 meg, then the proportionate set size of each is 100K, so it's the proportionate set of that. USS is, no, it's not the Starship. Its unique set size is how much memory is unique to this specific process with regards to the rest of the processes. So that's for librank. Procmem, so procmem, which is another one here. Let me actually do that with less, so that's going to give us a little bit more visibility. Oh yes, I need to give it a PID. Sorry, let me do this. PS system server, all right, 366, so I would do something like that, 366. This is going to give me the map of that process and how much memory is being used by each of the segments or parts of that process. Procrank is similar to librank, but what it does is it tells you the use of essentially the different sizes of the sections of the process, and so on and so forth. Now, once you've got the framework up and running, so once everything is up and running, you can use a bunch of different tools to see what's happening in the Java side. So, for example, I showed you service list. Okay, it gives you the list of system services. There's another utility which is really useful. It's called dumpsys, and it allows you to essentially dump the state of these various system services. So, using something like this, dumpsys status bar, I can ask the status bar, give me your internal state. All right, and if I do dumpsys without any parameters, something like that, it will show you the state of all the system services in the system, regardless, of what it is. Okay, and obviously there's a lot of information there. So that's a good way to grab a snapshot of some of the internal state. Now, overall, obviously those of you who are doing this on a daily basis are familiar with logcat. So if I do this shell, all right. Right, it died. Just give me 1 second. I'm going to force it to rescan itself and find the board again. Oh, come on. All right, I can't connect to the board anymore. No matter. I'll just go ahead with the emulator as it is. So adb-d-e, shell. And if I do something like logcat, I get essentially the content of the logs of my entire system. There are different parameters you can pass to logcat to see the other buffers if you want. So that's the architecture of logcat here. What I do want to show you, so for example, if you want to get live statistics on the system, there's a whole bunch of apps on the store that allow you to get some stats. We found those to be frustrating because they occupy the center of the visual while you're developing something else. So we actually wrote an open source tool which runs essentially a web server on the device and essentially just shows you the statistics off of a port number. We put that on GitHub. It's Apache licensed. You can do whatever you want with this. And if you select the process here, it'll show you the dump logcat of that process specifically. And if I switch to another one, it'll just give me the other ones. So that's a little bit more useful than something that uses your visual. Now, once the framework is up, there's a whole bunch of tools that you can use to actually interact with the system services. So for example, if you're not familiar with that, you should. AM is a tool that allows me to talk to the activity manager. If I want to send intents off the command line, I can do that, okay, with AM. PM allows me to talk to the package manager and so on. The trouble with those is they're ungoogleable. Try looking for AM in Google or PM in Google and you just won't find what you're looking for. But anyway, there's a whole bunch of those that you might want to take a look at that allow you to talk to the system services. I am going to skip over this because that actually is fairly well documented. I do want to show you symbolic debugging inside the native side. So I showed you the debugging side on the Dalvik. Let me show you how you can do it on the C side of things. So if I do something like, let me do this, GDB server. And then let me do localhost 2345, and I'm going to do service call. So essentially what I'm doing here is telling the GDB server to start this tool called a service call, attach to it, and wait for the host to start debugging this thing. So the other thing I'm going to do here is I am going to actually, just let me do this. I'm going to essentially also do some port forwarding so my host can actually connect to that port number on the target. So let me do that. So you can see he starts the process, he's listening to the PID, and now I'm going to do here is something like ADB forward, and then TCP 2345, TCP 2345. So essentially if I connect to 2345 on machine, it goes on the board, so to speak. And then I'm going to do something like, actually I'm using the emulator, am I not the actual other guy. So let me just make sure I'm using the proper debugger here. So ARM, Linux, Android, EABI, GDB. I am trying to debug out target product generic symbols system bin service. That's the process. Now I'm going to attach, it's the binary. Now I'm going to attach to the process using GDB. So target remote localhost 2345, bad name resolution, right? Localhost. So now he's connected, and in fact, if I go to the other shell, he should say that he's got a connection. Let me just go back to the shell. There we go, remote debugging from host. And now I'm going to set a breakpoint in my main function, okay? So I set a breakpoint in main, I say continue, okay? And now I'm stepping through my code. He's at line 70 here. I'm sorry, the window is a little bit small or big for you guys in the back, so let me kind of just minimize it. There we go. So I can do next, okay? Next. I'm now stepping through my code in my C side with the symbolic debugging. Okay? Now that's not too bad. What's even more interesting, though, is doing the same thing but with a live system service. All right? So essentially, or with any Java process that has a JNI counterpart. All right? So in other words, I'm calling C from my Java side. Can I set a breakpoint in there? Is that possible? And yes, it is. So let me show you that. So actually, quit. Yes, we're done. And let me also change the size of this window so you can see it in the back. All right, so I'm going to also do GDB server. So GDB server. And then this time I'm going to say attach. So oh, actually, before I do that, system server process. What's the PID of that? System server. So 366. So GDB server attach localhost 2345 on PID 366. So I am attaching to essentially the system server. All right. Now I'm going to go on my host. Okay. And the order of this is very finicky. So if you'll forgive me, I'm actually going to use my slides to cheat. So let's do this. ARM Linux that target remote localhost 2345. So now I'm attaching to the board. Okay, and he says remote debugging. And now I'm going to say, okay, file is out, target product generic. That's the file that's actually being debugged. So symbols system bin app process. I could explain to you what's happening here, why I'm using this one, not something called system server process, but that would be a longer explanation, so I'll get back to that later. I'm going to tell it where the dynamic linker is, set solib absolute prefix as being out target product generic symbols. All right, so now it knows where the symbolic linker is, and now let's tell it where the libraries are. Set solib, nope, set solib, and then the other one is search path out target product generic symbols system lib. Now it's going to load all the libraries up, okay, and the JNI code is in one of those libraries. It'll choke on Web Chromium or whatever, give it a second. It's a rather big library. In fact, if you build the AOSP, it's like 70% of your build time is Chromium building. So once it's done with that, I'll be able to set a breakpoint in my JNI side, all right? And then when I trigger the system service and it goes in the JNI side, I'll be able to step through my C code that's being called by my Java side. So in other words, if I had my Eclipse set up to have a breakpoint in the Java side, I could step from there into my C code. Obviously, in two debugging environments, there is not a single debugging environment that gives you both of those things in the same time. All right, there we go. So now I can set myself a breakpoint. So let's go for breakpoint com Android server power manager service 171. So I'm essentially setting a breakpoint in the Power Manager System Service. I just know this line number by heart because I do this demo very, very often. So, okay, continue. All right, and the way I'm going to trigger this guy is actually by pressing the power button here on the emulator because I'm running the emulator. And he should hit my breakpoint. He has, okay. I am in my JNI code, and I can now step in the JNI side of my system server process. Okay, so from that perspective, I can debug anything in the platform, right? System service, or if I want to just step through it for educational purposes. I want to understand, why is my application not doing what it's supposed to do, and what is it calling? I can do all of this using those mechanisms. So far, so good? I am debugging through the C code, that's right. Yeah. So if there was a corresponding Java call that was made before, I could break and point into that, and then follow from Eclipse into this side where I would be debugging the C side of things. Okay. The last thing I want to show you, because we've got like 3 minutes left, or something like that, is I want to show you the ftrace functionality. Let's see if I actually have any devices left connected to this thing or not. No, they're all dead. Give me just 1 second. So power cycle solves everything. Alrighty. Right. He should be there in a second or two. Come on. There we go. Okay. And let me type this. Sys kernel debug tracing. All right, for those of you not familiar with this, this is the ftrace functionality of the Linux kernel. And the ftrace functionality allows me to trace the Linux kernel's behavior dynamically. And that means I can get a tremendous amount of information. So let me show you a very raw example here. If I do echo function into current tracer, all right, and I do cat trace, I'm seeing here every C call in the kernel, one by one, with the timestamp and the PID where that call was made. So that's a lot of information, all right? Sorry? It is overkill, obviously. So this is like a very kind of like brief 2-minute demo of what ftrace can do, but knowing what you can do with this is the whole idea. Obviously, there's only so much I can demo you. Usually, a proper demo of ftrace will take me 2-3 hours, but I just want to show you that it's available. Because one thing I can do once I've got this is I can filter things down. I can say, I want to see this call, just this one, all right? I can say, I want to see all the calls to the right system call. So I can do something like this, echo sys right into set function, set ftrace function, filter function. There we go. And then echo nothing into trace. Now cat trace. I should see just the calls to syswrite. So all the system calls that are of write nature are now showing up in my trace, and nothing but that. I can see just the scheduling events. I can see the interrupts coming in, whatever I want. Okay? And the nice thing about ftrace is those events are logged as they happen. We don't have breakpoints here being done. We're not changing the behavior of the program. When I'm debugging something with GDB or anything like that, I'm altering the behavior because I'm stepping through my code. I am not stepping through my code here. I'm just recording it as it happens. And that's really awesome, because then I can essentially track everything happening. I can also say, all the scheduling changes, show me the scheduling changes, show me when am I scheduling to another process, and then a specific list of processes or operations being done in those tasks. Okay, so obviously I wanted to focus my demo here on, my presentation on demos, and I've spent a lot of time on that, but a lot of the stuff I just mentioned to you, which my computer just kind of went offline or something. Oh, there we go. So a lot of the stuff I showed you here is also in the slides, so you're welcome to go through them and kind of walk through those things yourself on your side on this board. Or on the emulator, but this board is really kind of worth your look. So I think we're out of time pretty much, right? Right on time, okay. So I am going to be here. Sorry? I have 1 minute. Any questions? I'm going to be around anyway till tomorrow. You can catch me in the hallway or whatever, or email me and we'll try to figure things out. Where are the slides? Do you know where the conference puts them? Makes them available? You don't? Yeah, in any case, sorry, go ahead.
I don't know the answer. I will get that figured out.
Okay, either way, this slide deck is a customized version of another slide deck that I've used 2 or 3 times before at other conferences. So like at NDevCon, I think I made this presentation. So if you go to slideshare.net/Opersys, it's one of those presentations. It has this. The video, I have no idea about that. I'm sorry. You'd have to ask the folks at the, I'd assume it's going to get posted. They will be posted? Okay, there you go. You got your answer.
When you were kind of coding in the terminal there.
That's right. I believe this is all being filmed. So, and whatever I typed here, I showed in the slides. That's the reason I kind of skipped a little bit of the slides, because essentially everything I've done on the slide, everything I typed is on the slides. So there's no point in showing you the same thing twice. Sounds good? Is there an issue with running multiple debuggers at the same time? Not really. That's right. Is there any like issue going from Java to C in terms of debuggers? Not so much. What I tried to look for is a debugging tool that gives you one thing that gives you all the layers, and there isn't one. The Lauterbach device gives you native Jtag integrated into the same environment, and that's cool, but they don't have the Java side of things. And as far as my understanding is that that's not possible, so they're not technically attempting to do that. They spent 2 years trying to, and I think they abandoned that, and as far as I understand it. Yes, sir?
We use the ARM DS5 for Eclipse.
Yes.
Okay,
Okay, DS5 works for Java and C++ integrated in the same environment? Does it? Okay, I should go take a look at that. Thank you, sir. ARM DS5, it's a tool that ARM makes. Yeah, so it's a tool that ARM makes available for people coding on ARM processors.
So running multiple debuggers shouldn't be an issue given we have multi-core architectures.
Sure, but does the multi-core aspect kind of influence the fact that we got multiple debuggers or not? I don't.
Kernel should be able to be smart enough, sophisticated at this point to
Sure, but even if I had a single core, this should not be an issue. No, the schedule will schedule things around. Yes, sir.
How can we actually debug which cores are active on multi-core devices and if they are active on which core an application runs?
Yes, okay, that's a good question, and it's a complex question. So how do I figure out which core is running which process? The only way you could do that is with something like ftrace. You could then say, okay, give me the PID, CPU ID, and record that for scheduling changes, and you would see, okay, process X is coming in on process ID XYZ, and that would give you that information.
Yeah, but then this one needs somehow to be correlated with
L.
the MD decision.
That's right, but the trace would give you that information. The trace has CPU ID, process ID, and event. So if you track the scheduling changes, you will get that information right there. All right, so we are out of time. Thank you again for your attention, and I will be around if you need more information.